Hi everybody. This is just a recap of what we did in class, and it'll be very brief, but hopefully help those of you that were absent. So this is lesson 15, recapping a little bit about rotations and reflections and talking about symmetry. If you notice over here, there's a triangle ABC, and it's been reflected in line L to become A prime, B prime, C prime. A prime, B prime, C prime was then reflected in line M by us in class. So we took this and we reflected it in line M. It turns out we did one reflection, two reflections, and two intersecting lines. Now I'm not very good at sketching what the reflection would have looked like, but the triangle would have ended up, let's see if I can draw it, would have ended up something like this. Mine's a little bit bigger than what it should be, but there's C double, B double, and A double. Alright, mine's a quick sketch, not an actual construction, but you guys in class had constructed it. If you look down here, hold on. A student looked at the image of the reflection, and basically if you read the parentheses, the student guesses that from the first triangle to the third, it's actually a rotation. And in class we said, would we agree? We said yes. Then they asked, what does S represent? Well, S turned out to represent the center point of the reflection. So you remember, the center point, for instance, if we were to measure the angle, we would connect C to S, and then S to C double prime. And then, if we were to measure the angle, we would take our compass, or protractor rather, and we would line it up on this angle and measure the angle. You could have done that between B and B double prime, or A to A double prime, and you'd get the same measurement. Down here, when you reflect a figure across a line, then reflect the image across the line that intersects first, your final image is a rotation. That's what we just learned above, of the original figure. Then, we recap a little. The center of the rotation is the point at which the two lines of reflection intersect. That's what we're referring to with S. Right here. As discussed in lesson 13, that was one of our previous lessons, the angle of rotation is determined by connecting the center of rotation, which we did, S, to a pair of corresponding vertices in the original, on the original and the final. So that's what we did here. Connect an original vertex to its image. Connect them both to the center of rotation, and then you get to measure. When we measured in class, measured the angle, we all had varying angles, but we were in the ballpark. I had negative 105. Some people had negative 90. Some people had negative 97. That's one way to write it, or you would represent it as, for instance, 105 clockwise, or 90 clockwise, or 97 clockwise. So to indicate that it's clockwise, you put a negative on it. Next page. So we talked about first, we started with the isosceles triangle here. If let's talk about the definition. An isosceles triangle has at least two congruent sides. Let me fill that in. It's important to say at least because that allows for the equilateral triangle to also be isosceles. It says here, every point on the triangle on one side of the line of symmetry has a corresponding point on the triangle on the other side of the line of symmetry, given by reflecting the point across the line. What line are you talking about? Well, we're going to sketch it. Sketch in the line of symmetry on this isosceles triangle and label it L. We don't have to actually construct it. They're giving us a chance to just sketch it. Take your straight edge and line it up, going straight down the middle. That's one line of symmetry. And you can see that it's a line of symmetry because on the left side, it matches the right side. If we were to fold the left over the right, S would map onto T. And then they went through an activity where they told us to make a point on our S and imagine where it would map on our T. Right there. If this was P, this would be P prime. And let's answer this question. Does every figure have a line of symmetry? No, some will not. And that might come up later in our lesson. Step 1 here. Anticipate, or basically guess, or figure out where you think a line of symmetry would be in this hexagon, which happens to be a regular hexagon. A regular hexagon, or any regular polygon, has all of its sides congruent and all of its angles congruent. So imagine a line were drawn and find 2 points that would map to each other when reflected over your anticipated line. So for instance, if I think that there's a line going straight down the middle here, I would imagine that F would map onto C. So I'm going to now construct the perpendicular bisector from F to C, which will actually give me the line of symmetry. And that's actually what you're going to do, and that's what we did in class. So take a minute to construct the perpendicular bisector, giving you the line of symmetry, and then I'll come back. Now, my line is the green one. I'm assuming, or I'm pretending that I constructed it. You constructed it using the perpendicular bisector between, for instance, F and C. Although you may have constructed it with a perpendicular bisector between maybe A and D, maybe you went between A and B, or maybe between F and E. There's many places you could have constructed it. Now we get to sketch any remaining lines of symmetry. So where else do you think there's a line? Maybe there's one here, one here. Sketch all the remaining lines of symmetry that you think exist. I'm going to do that as well. If you notice, there's one through the middle of each side, which I've done, and there's also one through the middle of each vertex, going directly across. And here's the center. Actually, it's the center of rotation. Now to count, how many are there? It's a little tricky. How many lines are there? I'm going to change the color for a minute. If we count the lines, that's one line. It's a second line. Third. Fourth. Fifth. And there's the sixth. There are 6 lines of symmetry. It's a little tricky to count. You'll eventually notice the pattern. There's one line of symmetry for each vertex. The next one says, this is an important one, this question right here. Take a look. Notice it's asking us to justify a justification question. Remember we spoke about that? How would we justify that the line we constructed, or any lines that we constructed, are in fact lines of symmetry? So think about what that means. If, for instance, this green line I constructed is a line of symmetry, wouldn't that mean that A reflects onto B, and F reflects onto C, and E reflects onto D? We actually did a reflection the other day. So the answer to this is, I'll put it in red, construct the reflection of a point. And what happens is, I'm going to go down here, see if it maps onto its image. I'm going to abbreviate here, but so basically I could take point A, actually do the construction of the reflection, and see if it maps onto B. Take my compass, put the point here, swing an arc through here, make an arc, center here, arc, center here, arc, and see if B lands where it should. That would be to justify, to actually physically prove it. Not a proof, but to physically prove it. The next thing we need, let me get a different color, is this question, which I've kind of covered up. This one right here. Talk about rotational symmetry. Well, line symmetry means basically the left is going to match the right. You have a point you can reflect over the line, and it maps onto itself. So rotational symmetry is this. I'm going to write it down, and you can copy it. Figure can be rotated instead of reflected. between 0 and 360 and map onto itself. I think the words give it away. Rotational symmetry. With line symmetry, we can reflect A onto B and it maps onto itself. With rotational symmetry, we can rotate the figure and it maps onto itself. If you rotate 360, you're back where you started, so that's not a big deal. We're not worrying about that. Okay, that's rotational symmetry. You can rotate the figure and it maps onto itself, or basically looks like it was. Let's go to the next page. This is where we left off in period 3, and I think we got halfway through, or almost all the way through in period 5. Okay, so on this page, the top part we filled in, I mentioned briefly on the other page, in the previous page, that a regular polygon, all the sides have the same length, and all the angles have the same measure. We basically speak about the sides and angles. The sides are all congruent, and the angles are all congruent. Now on to number 3. Number 3 over here. It says for each regular polygon, they're regular, so all the sides and angles are congruent. Determine the minimum number of degrees needed to rotate or turn the figure so that it maps onto itself. So for instance, with the octagon, you could take T, turn it to land on U, or you could turn it 1, 2 times to land on V, or turn it 1, 2, 3 times to land on W, like that. It's going to turn out for all these regular polygons, since all of their sides are the same and all their angles are the same, that you take the total number of degrees in a circle that you could rotate from beginning to end, that would be 360, divide it by the number of angles. Let's watch for the T, 1, 2, 3, 4, 5, 6, 7, 8. I could make 8 full rotations and get back to where I started. Therefore, you take the number 360 and divide it by the number of sides, n being the number of sides. So for the equilateral triangle, it's 360 divided by 3. For the square, 360 divided by... And for the regular pentagon, 360 divided by 5, etc. You guys can figure these out, and you're going to fill these in and finish that for homework. Now down here, how many lines of symmetry does each have below? If it has at least one, construct one line of symmetry. Remember, when we construct a line of symmetry, to construct it, we do a perpendicular bisector. One perpendicular bisector. I ran out of room. But you pick 2 points where you believe that the line of symmetry falls between, and you do the perpendicular bisector between those points. For instance, with the rectangle here, I would imagine, and you can see the same thing I'm sure, that there's probably a line of reflection between the G and H. So construct a perpendicular bisector between those 2 points. Now, as far as this figure goes, looks like it might be a rhombus. Be careful when you are imagining, sketching, or constructing the lines of reflection. If I were you, I would construct and then check, oh, there's the bell, by reflection, just like we spoke before. So for instance, if you think there's a diagonal line, I would construct it and then take K, physically construct the reflection of K, see if it lands on M. Okay? And let you guys work on those. Let me peek at the next page. The next page, find the center of rotation. We did that the other day. Find the center of rotation. We spoke about that, and it was actually in our Plickers game, so if you remember what we did today. Center of rotation, look it back in your notes. It's very easy. Look in your notes on how to find that. Then, answer the questions here. The center of rotation of an equilateral triangle is also the blank. So I'm going to give you a little hint. You're going to bring up Courtney. Courtney probably buys odd animals, causing mayhem in a barn. There you go. You're going to need one of those for that. And I will let you finish up the rest of this for homework, because I don't think you need anything else from me. Let's check this page. Yep, it's all should be self-explanatory. So good luck, and text me if you need me. See you in class.